In the previous chapter, we looked at the structure of aromatic compounds, what makes a compound aromatic, and we looked at the explanation for why they're aromatic. In this chapter, we're going to look at reactions of aromatic compounds, and in particular, the most important reaction that we're going to look at is electrophilic aromatic substitution. It is the characteristic reaction of aromatic compounds like benzene. So we can do electrophilic aromatic substitution. You'll see it referred to as EAS. And in this process, we'll have a hydrogen atom that is replaced by an electrophile. All right, so we have a good electrophile that comes in and replaces the hydrogen, and then our hydrogen is removed at a later point. Since benzene is especially stable, in order to do this reaction, we need to regenerate the aromatic ring. So it temporarily disrupts the aromatic ring, but then we regenerate that aromatic ring before the reaction is over. Now, one important note here is that when we do this reaction, we can't do just regular addition reactions to aromatic rings. If we attempt to do addition, for example, of Br2 across a carbon-carbon double bond on an aromatic ring, we're going to find that that reaction ends up being endothermic. And that's because we would be breaking up the aromaticity that we have here. And as you recall, the difference between this conjugated diene and this aromatic ring is it's about 150 kilojoules per mole. So that would make almost any reaction that you did endothermic. Well, addition reactions that are endothermic don't work. I'm going to say that again. Addition reactions that are endothermic don't work. And this has to do with the entropy. When you have an addition reaction, the entropy is going to decrease. And if you have a negative value for delta S and a positive value for delta H, the heat, the enthalpy, you're going to end up getting a value of delta H that is just not possible, or delta G that's not possible. So if you go back and look at thermodynamics, you'll find that endothermic reactions for addition reactions, they just don't work. So we have to retain that aromatic ring at the end of the reaction. It doesn't mean that we can't temporarily break up the aromatic ring, but when we get to the end, we have to have that aromatic ring intact. So there are many examples of electrophilic aromatic substitution that we're going to talk about in this chapter. We will talk about halogenation. With halogenation, you'll see that's in the next section. With the halogenation, we will see that we can substitute a hydrogen with either chlorine or bromine. Nitration and sulfonation, we group those together because of the similar mechanism. Here we replace a hydrogen with a nitro group or a hydrogen with the sulfonic acid group. And then we'll also look at Friedel-Crafts Alkylation and Acylation. So Friedel-Crafts Alkylation and Acylation. And we group those together because of their similarities as well. So let's look at the generic electrophilic aromatic substitution mechanism. Regardless of which of the 5 reactions I just showed you, halogenation, nitration, sulfonation, Friedel-Crafts alkylation, or Friedel-Crafts acylation, so regardless of which of those we use, there's going to be a 2-step mechanism. In the first step, we're going to add an electrophile to the benzene ring. That's going to create a resonance-stabilized carbocation. This type of carbocation that's resonance stabilized like this, we refer to as an arenium ion. I don't know if your book uses that term, but that's the term that's used in most textbooks. So this is the arenium ion. All right, that's the first step. And then in our second step, we deprotonate the hydrogen with a base to reform the aromatic ring. So It's okay to temporarily disrupt the aromatic ring, but we have to reform it at the end if we want this reaction to work. So we're going to look at that step 1 a little more closely. What is that resonance stabilized carbocation that we have formed? So in that first step, the electrophile reacts with the benzene ring, and in order to help us with this, to make sure that we understand what is going on, it's really helpful to keep track of where the positive charge is, and it's also helpful to leave the hydrogen on there, draw the hydrogen where your electrophile is going to. That way, that'll remind you that that is an sp3 hybridized carbon, and that we can't draw any double bonds going to this carbon. So that's important. So you just find one of the double bonds, you put the electrophile on there, include the hydrogen where the electrophile went, just so you know it's sp3. And then here, we put a positive on the other carbon that had the other carbon that was in that double bond. Then we can draw the resonance structures for this, where we move the double bond around and in turn also move that positive charge around. All right, there's something that's kind of interesting when we do this. You'll notice that the positive charge ends up being on every other carbon when we look at the different resonance structures. It's either in the ortho, the para, or the other ortho position, or if we want to think of it in terms of numbers, the 2, 4, and 6 positions on the ring. Now, it's no longer an aromatic ring, it's an arenium ion, but we can still think of it as ortho and para, because we're going to regenerate that aromatic ring pretty quickly. This is what the hybrid structure looks like. So we have a positive charge on 2, 4, and 6. So that means we have a partial positive charge on carbons 2, 4, and 6 in our hybrid structure. All right. Here is an energy diagram for electrophilic aromatic substitution. This energy diagram looks very similar to some of our other two-step mechanisms that we've talked about before, like the SN1 or the E1 reaction. And there's quite a few similarities, right? First of all, overall, it tends to be an exothermic reaction. Endothermic reactions tend not to be as favorable. So it tends to be an overall exothermic reaction. Our starting materials are here, and we include the electrophile. Sometimes we have to generate that electrophile in a previous step. We'll talk about that. But that's our starting material. Our intermediate is much higher in energy. So our arenium ion, here is our hybrid structure of the arenium ion. And you'll again notice that's an endothermic reaction and has a fairly large activation energy. Our second step is simply the removal of this hydrogen and the reforming of our aromatic ring. That tends to have a fairly low activation energy and also tends to be fairly exothermic to make up for this endothermic reaction. Because the first step has a large activation energy, we will find that the first step is the rate determining step. So it's going to be what determines how fast this reaction goes. One other thing before I move away from this page, one other thing I want to mention is that because the rate determining step is endothermic, that means, according to the Hammond postulate, and if you're not familiar with the Hammond postulate, go back and look at one of my other videos. According to the Hammond postulate, this transition state is going to more closely resemble the product of the step. In other words, the intermediate in this reaction. Again, because it's endothermic, the transition state will resemble that thing it's closer in energy to. And so anything that helps to stabilize this is going to help stabilize this and therefore speed up the reaction. That will become important later when we're talking about electrophilic aromatic substitutions on substituted benzene rings. That's coming up several sections from now. So let's look at halogenation. We're going to start, we'll start with the simplest one, halogenation. It's fairly easy to do. In this, benzene reacts with either chlorine or bromine. And if you have chlorine, we need to use the Lewis acid, iron 3 chloride. And for bromine, we need to use iron 3 bromide. And we can get chlorobenzene or bromobenzene, respectively. So there are the products of those. All right. Now notice that I didn't include either iodine or fluorine. They're just not synthetically useful. For iodine, it ends up not really being very reactive. It ends up being an endothermic reaction. It just makes it not very helpful. So it's difficult to do with iodine, so we just don't do it. With fluorine, if you just put fluorine in with benzene, it's just violently reactive, and you probably don't even want to be in the same room when we're doing it with fluorine. And so you can't do single substitution with fluorine. And so I don't know, if you ever meet a fluorine chemist, like, be kind to them, because they have a rough time with things. Doing fluorine chemistry can be fairly exciting. All right, so let's look at that bromination mechanism, and we'll find chlorination mechanism is identical. We're actually going to do the chlorination mechanism as an example on paper here in just a few minutes. So Lewis acid-base reactions with bromine and iron 3 bromide, we get that Lewis acid-base reaction where we form this reactive electrophile. So this thing is what acts as the electrophile. You'll notice that there is a positive charge on this bromine, but it's actually the bromine here on the outside that is the electrophilic bromine, the one that reacts with the halogen. That means that this positive charge is pulling electron density away from it, making this one have a partial positive charge on it. In any case, it is the electrophilic one. Similar to the way that bromine reacts with an alkene and forms the bridge bromonium ion. If you don't remember that, go back and look at chapter 8, and you can look at the bridged bromonium ion. Chapter 10. All right, addition of our electrophile. So we'll get addition of the electrophile to the carbon-bromine bond, and that's going to form our resonance stabilized carbocation, which is our arenium ion. So we'll get this, 3 different resonance structures there. And then finally, we're going to get deprotonation of the arenium ion to form our aromatic ring. So first step, this is the one that's endothermic, the one that curves up. This is our intermediate, so that dip in the middle of our energy diagram. And then this is our product, so we have a big exothermic step going down. Let's look at number 3. All right, so we want to draw a detailed mechanism, all right, for the chlorination of benzene using chlorine and iron 3 chloride. We're going to start by reacting the chlorine with the iron 3 chloride. This will be just like the one we saw a minute ago. And if you need to, you can go back and look at the mechanism that I had in the presentation a minute ago. So FeCl3, and that's going to give us FeCl3. All right, and so I have a positive there, a minus there, and then I'll go ahead and put all these electrons in. All right, so negative on the iron and a positive on the chlorine. All right, so now let's draw our aromatic ring. All right, so we'll draw that aromatic ring, and we'll have our chlorine. All right. this is our electrophile. And so we're going to take one of these pairs of electrons and we'll go, it's a double arrow there. So we're going to go to that chlorine and then we'll break this bond between the two chlorines. Go ahead and put that hydrogen in there. So, so we now have this. We have two additional resonance structures that we can draw. One, we move that pair of electrons. So we get a positive charge at the 4 position. And then we'll move the pair of electrons again. All right. And then, I'll just go this way. We're going to use the FeCl4 minus. Right, we're going to use that. So typically when I do this mechanism, and you'll find the same thing on the presentation, typically we just take this pair of electrons and we go to the hydrogen, and then we'll take this pair of electrons and put it there. And so that's going to give us chlorine plus HCl plus the FeCl3. And that would be our 3 products there. This is our main product. These are some byproducts. This is actually a catalytic because we started with it and it's regenerated. So, all right, so that is our detailed mechanism. All right. So there are a couple of interesting biologically active aryl chlorides. So there are some times where they'll take a compound and they'll add a chlorine to it, and that will change the reactivity of it. It'll change the biological activity of it. This particular compound is an antidepressant, well-known antidepressant, bupropion, not prion. This one, the chlorpheniramine, it's the common brand name for this is chlorotrimethon, and that is a commonly used antihistamine, over-the-counter antihistamine. These particular compounds are defoliating agents, so you can spray these on plants and it will kill the plants. They are particularly potent at killing the plants. Interestingly, these by themselves have relatively low reactivity. However, one of the byproducts are fairly low risk, so they're fairly low toxicity for humans. However, one of the byproducts is very dangerous, and so one of the byproducts when they're forming this, particularly this one, is that they get this dioxin. It's the 2,3,7,8, so 2,3 and the 7,8 positions, tetrachloro dibenzopyridioxine. So the dioxine is this part, and then this are the dibenzo part, and then there's the tetrachloro. This shows up in about 2 or 3 parts per million when they're producing these compounds. And that 2 or 3 parts per million, that is enough for the pretty potent carcinogenic properties of this. Well, the reason I mention this is that during the Vietnam War, the the American military forces, under the direction of the U.S. government, sprayed about 20 million gallons of this mixture onto plants, trees, forest throughout the country of Vietnam. In doing that, they exposed tens of thousands, perhaps over 100,000 American soldiers to this compound, and millions of Vietnamese citizens and soldiers were also exposed. So very long-term negative side effects from this particular small microscopic impurity that turned out to be quite dangerous. So pretty horrible, pretty horrible consequences. So as we know, war is pretty horrible, and sometimes it can be even worse. All right, so that is chlorination and bromination, very synthetically useful. Of course, we can use it for bad things as well, but it is synthetically useful for many applications. Now we want to look at nitration and sulfonation. We group these two together because of the similarities of their formation and their mechanisms. But they are different groups and have different functionalities, but they have similar properties when we're making them. All right, so if we take benzene, we can treat benzene with nitric acid. So we take concentrated nitric acid and put it in with concentrated sulfuric acid, and we can do nitration. And then one particularly useful thing about this is we can take that nitro group and produce this aniline group using a reduction mechanism that we will talk a little bit later in this chapter. It's not actually chapter 18. This is an old graphic. It's in this chapter, chapter 16. We can also do sulfonation by a similar mechanism. Here, this is concentrated sulfuric acid. Sulfur trioxide, interestingly, if you take sulfur trioxide and mix it with an equal number of moles of water, you'll get concentrated sulfuric acid. A very exothermic reaction on top of that. Well, if you take the sulfur, so it's like, this is the acid and hydride of sulfuric acid. If you take this sulfur trioxide and put it into concentrated sulfuric acid, it's like concentrated sulfuric acid with extra acid in it. We call this fuming sulfuric acid, and I think it's kind of funny. Fuming, you'd think, oh, must have fumes coming off of it, which it kind of does, but also it makes me think, oh, it must be angry. Well, that's really a good description for this mixture. It's a very dangerous mixture to work with. So something you definitely want to know what you're doing when you're working with either of these. Both of these are quite dangerous. But the whole point of this is that we can do these reactions fairly easily using electrophilic aromatic substitution. So before we move on to looking at the reaction, we're going to do an example of the mechanism with the sulfur trioxide here in a minute, but I want to show you the mechanism for generating the electrophile. And for both sulfonation and nitration, we need to use the strong acid, concentrated sulfuric acid, to react with our other compound. In the case of with the nitric acid, we protonate that nitric acid. So we don't normally think of nitric acid as being a base, but in this case, with that huge excess of sulfuric acid, we can protonate that nitric acid and create this intermediate. That intermediate is unstable. You can break the oxygen-nitrogen bond here, get water and the nitronium ion, and the nitronium ion, here's a picture of it. The nitronium ion is what acts as the electrophile. So we'll look at that here in just a moment. For the sulfonation, for sulfur trioxide, it reacts and produces the electrophile, which is this particular electrophile. So once we have generated that electrophile, then that would react with the aromatic ring. So we're going to do this mechanism on number 4. We're going to do it with a substituted benzene, toluene. So let's switch over. All right. And so I'm going to do the first step up here, which is the generation of our electrophile. All right, so there is our sulfuric acid and our sulfur trioxide. That sulfur trioxide gets protonated. All right, so there we have reacted this with that, and that gives us our sulfonium ion. That is going to be our electrophile, which will react with our benzene ring. You'll notice here that we only have the para substitution product. It is possible to form the ortho substitution product and not so much on the meta. We'll talk about why that is later in this chapter. But we're just going to draw this mechanism to form this one particular product. All right, so rather than draw out this whole thing, our arrow is going to go to this sulfur. I'm going to draw this like this, SO3H plus, and know that when I draw that, I mean this. And we're going to draw the arrow going from this pair of electrons directly to that sulfur. So we'll go from here to that sulfur. All right, and here we've got a positive charge there. I'll go ahead and put this hydrogen in so that we can keep track. So hydrogen, SO3H. All right, so now that we've got that, let's draw the 3 different resonance structures, one where the positive charge is here and one where the positive charge is there. So we'll start by moving this pair of electrons All right, and then we've got one more resonance structure. All right, and so that is our third resonance structures. We'll take those 3 resonance structures. Again, the true structure is a hybrid where we have a partial positive charge here, there, and there. And so now what we want to do is we want to deprotonate this to form our product. So we're going to deprotonate that, and we're going to use we'll use the conjugate base of sulfuric acid, which is the bisulfate ion, so O SO3H minus, go here to that hydrogen, and then we're going to take this pair of electrons and form the double bond there. Here, I'll go ahead and draw it out so you can see what it looks like. All right, and there's a whole bunch of lone pair electrons on those oxygens. And then, so plus H2SO4 is regenerated here. All right, so that is the mechanism. One thing that I want you to pay attention to when you're thinking about this in terms of substituted benzenes is that this particular resonance structure is important because of that alkyl group. Again, we'll talk about that a little bit later when we talk about substitution patterns. All right, so we've talked about halogenation, nitration. Now, I didn't do a mechanism for nitration, but it's almost identical to the sulfonation, and I think you'll see one of these on one of your homework problems. We now want to look at Friedel-Crafts alkylation and acylation. With the Friedel-Crafts alkylation and acylation, so yes, we'll start with the alkylation. We'll talk about acylation here a little bit later, but we'll talk about alkylation first. We're going to treat benzene with an alkyl halide, an alkyl chloride to be specific, and aluminum chloride. And that's going to form an alkyl benzene. So here is the generic reaction where we take an alkyl chloride plus aluminum chloride, and then that gives us the alkyl benzene plus HCl. This is a more specific reaction. It's an example here. So tert-butyl chloride plus the aluminum chloride, there's the benzene, and then we form this tert-butyl benzene plus HCl. So let's look at the mechanism for electrophile formation. Now, I want to point out that there are two different mechanisms. There's a mechanism that you have for methyl and primary alkyl halides, and we have a different mechanism for secondary and tertiary alkyl halides. So with the primary and methyl alkyl halides, the aluminum chloride reacts with the chlorine in a Lewis acid-base reaction. So this is a Lewis acid here, this is a Lewis base, and we form a Lewis acid-base complex. That acid-base complex is the electrophile. It does the reacting directly with our aromatic ring, and so it stays like this until it reacts with the ring. When we have secondary and tertiary alkyl halides, the aluminum chloride again reacts with the alkyl halide to form that acid-base complex, but then that breaks apart. We break the carbon-chlorine bond heterolytically, so the pair of electrons goes with the chlorine, and we form a carbocation electrophile. Now, you're familiar with carbocations if you've gone through all the lectures up to this point. You're familiar with carbocations, you've seen them before, and you understand some of the advantages and some of the challenges of working with carbocations. All right. So here we're going to look at this example in a little bit more detail. We're going to look at the mechanism of that, where that tertiary carbocation reacts with the benzene ring to form our resonance stabilized carbocation. Again, this is the arenium ion. All right. Then the AlCl4 will deprotonate. We'll take both of the electrons, just like what we did with the iron chloride a little bit ago. We'll take both of those electrons and go to the hydrogen, break this carbon-hydrogen bond, and then reform our aromatic ring. We'll get HCl in the process and aluminum chloride. So technically, aluminum chloride here is a catalyst, technically. There's a couple of interesting facts about Friedel-Crafts alkylation that you need to be aware of. First of all, this only works with alkyl halides where the carbon that is attached is sp3 hybridized. If you attempt to do this with a vinyl halide or an aryl halide, it's going to be unreactive, so you're not going to have much luck there. All right, so it just won't work with these things. Now, there are other things you can do with these, but you can't do this. When it comes to rearrangements, anytime you form carbocations, rearrangements are definitely possible. Here are a couple of examples of some rearrangements. If you start with this particular secondary alkyl halide, you can get a rearrangement that will result in the formation of a tertiary alkyl halide and resulting in a quaternary carbon, which is this. So you'll get a slightly different substitution pattern from what you may have been expecting. If you have a primary alkyl halide, you can also get rearrangements. You can get a rearrangement here where instead of getting substitution at this carbon, you get substitution at the secondary carbon. Both of these occur via a 1,2 hydride shift, although the mechanisms for these look a little bit different. We're going to talk about those in a few minutes, but for now, we'll just say that they do a 1,2 hydride shift. So let's look at number 8. Number 8 is really easy. So the question is, which halides are unreactive in a Friedel-Crafts alkylation reaction? Really, we're just looking for, is the halogen on an sp2 or an sp3 hybridized carbon? And so because this one is sp2, this is unreactive. All right, because this one is sp3, it is reactive. So you can do Friedel-Crafts with that one. On this one, this particular carbon is sp2, so it is unreactive. And this one is sp3, so it is reactive. All right, so there's all kinds of interesting reactions you can do with these, but these you just can't really work with it. Let's look a little more closely at those rearrangements. So we're going to start with the rearrangement where we have the secondary alkyl halide, or secondary chloride, alkyl halide. So we form the acid-base complex here. This breaks apart, so we heterolytically break that carbon-chlorine bond to form a secondary carbocation. And then, because there is adjacent to it a hydrogen that is on a tertiary carbon, we can have a 1,2 hydride shift, and that will form a tertiary carbocation. And then the addition of the tertiary carbocation goes by the usual mechanism. It reacts to form our resonance stabilized arenium ion. Right, and then we get deprotonation to form our product. So that's how we go from where we think we're going to attach with this carbon, but we actually end up attaching with this carbon. So we get a 1,2 hydride shift. And here's the deprotonation step. For our other one where we had a primary alkyl halide, you may be wondering, well, how did we get a rearrangement there? Because we can't form primary carbocations. And that's true. We don't form a primary carbocation. Because it's impossible, or at least very difficult to form primary carbocations, we do form the Lewis acid-base complex between aluminum chloride and our alkyl halide. But then we get this reaction where we get the 1,2 hydride shift at simultaneous breaking of this carbon-hydrogen bond, forming a new carbon-hydrogen bond, and breaking this carbon-halogen bond to form this secondary carbocation. And then that secondary carbocation can go on and react as an electrophile with our benzene ring, and then deprotonation, as we have seen previously, to give us our product. So it's slightly different because we can't form that primary carbocation, but it's essentially the same thing. It gives us a more stable electrophile, and that more stable electrophile is going to be a little easier to use. So this happens fairly quickly. All right, there was one other thing that I mentioned about electrophilic or the Friedel-Crafts alkylation, and that is we can use other functional groups that form carbocations as starting materials. We don't necessarily have to use an alkyl halide with aluminum chloride. There are other possibilities. For example, we know that if we take cyclohexene and treat it with sulfuric acid, we can form this secondary carbocation. Because HSO4- is not a good nucleophile, in fact, it's a very poor nucleophile, it's not going to come in and react with that secondary carbocation, and so this is free to react. So we can do alkylation with this, Friedel-Crafts alkylation with it. All right. Another way, we talked about this back in chapter 9 when we talked about alcohols. We can protonate the alcohol. Protonating that alcohol will generate this reactive intermediate, which will lose H2O to form this tertiary carbocation, and then that can go on to react with an aromatic ring. So knowing this, we want to look at a couple of different reactions where we don't use aluminum chloride. Instead, we use other methods, and you'll notice both of these are sulfuric acid, and all the ones we're going to look at are sulfuric acid, where we generate our carbocation in a different way. So let's go back over here. All right, I'm going to pause the video to get the camera a little closer. All right, well, sorry for the little jump cut there, but this is a little bit zoomed in, so it's a little easier to read. Hopefully that will be helpful. All right, so we're going to, essentially, we're adding whatever our electrophile that's created from this to this benzene ring. And so all of these benzene rings are just going to have a substituent on them. And in this case, it will be a cyclohexane or cyclohexyl substituent. So this would be a cyclohexyl that's attached to that benzene ring. All right. Here, our carbocation would form at this carbon, so we would have a tertiary butyl group. And so we would form that. In this case, our carbocation is going to form here. So again, we'll have a it's not tert-butyl, but we'll have a tertiary carbocation. So we'll get that. And in this case, we're also going to form a secondary carbocation. So we're going to get the same product that we had up here. And so those will be the products of this particular reaction. So we now want to look at Friedel-Crafts acylation. It's very similar to the alkylation invented by the same people, Friedel and Crafts. This is a slightly different way of doing making a new carbon-carbon bond. But in this case, we're going to attach an acyl group to the benzene ring. And an acyl group is just a it's a carbonyl, so we're forming a new bond between the benzene ring and a carbonyl. And so in this case, that means we're going to form a ketone. So if we have this generic acid chloride, we will form this ketone. In this case, we've got the acetyl chloride, and we will form acetophenone as our product. So because that new group is bonded to the benzene ring, it's called acyl. That's why we call this acylation. All right, so now let's look at the acylation mechanism. So when we're doing the Friedel-Crafts acylation mechanism, the first step is essentially the same. We're going to form a Lewis acid-base complex. So the Lewis acid aluminum chloride will react with this chlorine atom, will form this complex. That complex is unstable, so we'll get heterolytic cleavage of this carbon-chlorine bond. And that when we get that heterolytic cleavage, we'll form this resonance stabilized acylium ion. One of them has the positive charge on carbon. One of them has the positive charge on oxygen. This one is probably the better resonance structure because everything has an octet, but this is the one that we are going to consider when we're thinking about it acting as an electrophile. It is the carbon that is acting as the electrophile. That carbon goes on to react with a benzene ring, and we have that two-step mechanism, much like what we would observe, in our previous reactions, our previous electrophilic aromatic substitution mechanisms. Don't worry, we are going to do the mechanism. All right, so now for intramolecular Friedel-Crafts. So intra means within. We can do, if we have both the aromatic ring and an acid chloride present in the same compound, we can treat that compound with aluminum chloride and do intramolecular Friedel-Crafts reactions. In doing so, it has to form a ring that's possible. So usually it just goes here on the adjacent carbon. And in this case, it's very useful. It's very useful to keep track of where the carbons are, like count your carbons. So like 1, 2, 3, 4, and you come over here 1, 2, 3, 4. So you don't lose track of your carbons. This is very important when you're drawing out a mechanism, particularly if you draw that mechanism on a test. All right, you can use this for all kinds of examples, and it seems like I give so many examples where it's the synthesis of illicit drugs, and so here is another illicit drug, LSD. So if you start with this compound, you can do the aluminum chloride. The aluminum chloride can react with that acid chloride, form the acylium ion. This carbon can come in and do an intramolecular Friedel-Crafts acylation to give us this intermediate, and then this intermediate, along with a few other steps, can go along to give you LSD. In case you're wondering, I don't know what these several steps are. If I did, I wouldn't tell you what those several steps are because I don't want you trying this at home. So yes, don't try this at home. All right. But I do want you to know how to do the mechanism. I don't want you to make dangerous things, but I want you to know how to do the mechanism for these. So we're going to look at the mechanism for doing Friedel-Crafts alkylation, intramolecular, and we're going to have a rearrangement at the same time. So this is good stuff here. All right, so first things first. If you have an acid catalyst, usually the first thing that's going to happen is you're going to protonate. So I'm going to put the lone pair of electrons there, and then we will protonate. All right, we're going to go from that lone pair of electrons to our hydrogen. And then we'll take that pair of electrons and it will go to the oxygen to give us the conjugate base of sulfuric acid. So now we've got the protonated version of this compound. All right. Now, before we go any further, because as soon as you start to dig into this, you're going to see some stuff that it doesn't quite seem right. There's something that the carbons don't seem to add up properly. So I think it's useful to go through and count these out. So number these carbons. 1, 2, 3, 4, 5, 6. And now we're going to come over here and we'll find the analogous carbons here. So 1, 2, 3, 4, 5, and it doesn't matter which one of these we call 6. But you'll notice here our OH, which is where we're going to form a carbocation, is on carbon 5. But carbon 5 is not the one that ends up attaching. And so that tells us that there must be a rearrangement that's occurring. So once we form a carbocation from this, we'll have to pay attention to what causes the rearrangement. So again, I'll number these 1, 2, 3, 4, 5, 6, just so we can keep track of where everything is. So let's lose H2O, and that forms a secondary carbocation. Make sure everything's on the page here. So we have a secondary carbocation there and there. And this is the stage. We have the secondary carbocation. If we get a rearrangement, it's because we're going to a more substituted carbocation. So we're going to take one of these methyl groups. It doesn't matter which one we take. And again, I'm going to label these. So we're going to take one of those methyls that's on carbon 4, shift it out to carbon 5 using a 1,2 alkyl shift. So it'll go to carbon 5, and when it does that, we now have a positive charge on carbon 4. 1, 2, 3, 4, 5, 6. So carbon 4 is a tertiary carbocation, and that's more stable. So the driving force to go from here to here was that we get additional stability. All right, now we're going to do the Friedel-Crafts. We're going to react it with this carbon. And so when we react with that particular carbon, we're going to go from this pair of electrons to carbon 4. All right, and let me go ahead and count these out. So 1, 2, 3, 4, 5, 6. And we have a methyl on carbon 4 and a methyl on carbon 5. So those are those two methyls there. I goofed up because I want this to have a carbocation. I wanted it to be the intermediate. So we do have a hydrogen that is there and a positive charge that is there. Now I'm going to draw the resonance structure. I'm not going to draw the resonance structure. I'm going to put that there are two additional resonance structures. All right. And then here's a little surprise for you. I'm actually going to cross that out, and we have 3 additional resonance structures. The other additional resonance structure involves donating a lone pair of electrons from here. We will look at that later in the chapter. But now it is just a matter of deprotonating this particular hydrogen, and when we do that, we'll reform our aromatic ring, and we'll get this as our product. So we just need our base, which is the OSO3H minus. We'll go from that. I'm going to have to kind of come around here. And then this will form a double bond there. And we will get this particular product. All right, and so that is our mechanism for doing this, and we will talk about how this substituent actually helps with this particular reaction a little bit later. All right, and before we go on to the next section, we're going to stop this video, and in our next video, we're going to talk about substituted benzene rings.